This is the first video for IB Quantum Mechanics, and we're going to start off by talking about an experiment called the photoelectric effect. The photoelectric effect is very, very simple. With most metals, if you shine a light on them, it sometimes will eject electrons, which is not a terribly surprising result. It happens because light carries energy. If it gives enough energy to an electron, that electron will break free of the surface. And around 1890 or so, Robert Millikan devised an experiment where he shined monochromatic light, that means only a single wavelength, on a metal, I think he used zinc, and then measured the resulting current. His setup looked something like this diagram here. This is a vacuum tube here, so it's a vacuum. There are two plates of metal, and the idea is that electrons get knocked off of this one, travel over here, and they flow through this ammeter back to where they started. And so with a very sensitive ammeter there, they can measure the photocurrent. But what Millikan did is he applied a potential difference, a reverse voltage, in the circuit. The result is that as you turn up the voltage, what happens is the current decreases. And we want to talk a bit about the stopping potential. The idea is that you have an electron that's knocked off the metal by the light, and it has some kinetic energy K. If it's going in the right direction, and some of them are, some of them aren't, eventually it will hit the other electrode because it's a vacuum, there's no air for it to get in the way, and that will cause a small electric current. But if you've got a potential difference between the electrodes, what happens is the electron is going to slow down and stop. And if that potential difference is equal to K over Q, then the electron will not reach the other electrode. Remember, the definition of voltage is equal to energy divided by Q. Now, if the energy is equal to K, then we call that the stopping potential. And the stopping potential is whatever the potential is required to keep the electron from getting there. The other important quantity you need to understand the photoelectric effect is the idea of the work function. The work function is the minimum energy required for the electron to escape from the metal, because the electron is bound to the metal. It can move around within the metal, but it can't leave unless you give it this amount of energy, phi, the work function. And the idea is that the electron gains energy E from the light. Phi of that energy goes into breaking it free, and the rest becomes the electron's kinetic energy. And what we find is that different metals have different work functions. Zinc, I think the work function is like 1.6 electron volts. Most metals, it's a little bit higher. Now, classically, we know that light is a wave, and we know that waves can carry any amount of energy you want because the amplitude determines the energy. The higher the amplitude is, the greater the energy is carried by the wave. And so what we'd expect to see are three different predictions from this model. The first prediction is that as the potential is increased, the current should decrease, but won't ever actually reach zero because there will always be a few electrons with very high energies. The second prediction is that brighter light should result in more electrons and also electrons that have higher energies. And the third prediction from the classical model is that the wavelength of the light shouldn't matter because that has nothing to do with energy. And it turns out that all three of these predictions turn out to be wrong. The first strange result has to do with the stopping potential. If we plot the photocurrent versus the stopping potential, classically what we'd expect to see is a smooth curve that asymptotically approaches zero. But what we actually see is a curve like that that reaches zero at a particular point. So the observation shows that, and we call this the stopping potential, and that tells us that there is a certain limit to how much kinetic energy any electron can have. And that maximum kinetic energy is equal to Q times Vs, where Vs is the potential that makes no current at all. So that doesn't agree with the classical hypothesis. The second disagreement we have with the classical hypothesis is that maximum kinetic energy does not depend on the brightness of the light. Once again, if you plot current versus the stopping potential, let's say you used dim light. And then you try it again using bright light. The bright light is going to produce more electrons for any particular value of Vs, but the exact same Vs gives you zero current in both cases. So that tells you that the brighter light doesn't result in any increase in the energy of the electrons. It just means you get more electrons, but they have the same energy. And the third result is that increasing the frequency of the light increased the maximum kinetic energy, which is weird. Classical mechanics says that shouldn't happen. This time we're going to plot stopping potential versus the frequency of the light. And what we find is that the graph is linear. And there's a certain cutoff frequency, and light of frequency smaller than that doesn't produce any electrons. And this graph is linear, and the weird thing is if you use a different metal, the graph is still linear with the exact same slope. No matter what metal was used, the slope of the line was equal to 6.626 times 10 to the minus 34 joule seconds. That is something that we call Planck's constant, h. And the only thing that changed is the x-intercept. And so that tells us that the x-intercept has something to do with the work function. And I hope that what you're gradually arriving at is that the energy that the light gives electrons is closely related to the frequency and wavelength of the light, not to its intensity. That is the big result of the photoelectric effect that you need to know. You need to be able to explain the classical hypothesis, all three of its predictions, and you need to know how the actual observations from the experiment did not meet those. In our next video, we're going to introduce the theory of quantum mechanics, which does explain these results very, very well.